All right, welcome back. This is lecture 9 in our series for the Intro to Markov Chains. This will conclude our discussion on the introduction for Markov chains. In the next series of lectures, we'll start asking more sophisticated questions about the Markov chains. But in this conclusion, we'll just get familiar with computing certain probabilities. And then in the future series of lectures, we're going to start thinking about different things, such as what happens when we run the Markov chain for a long time, or what's the probability that will be at a, especially what's going to be the probability that will be there, that will be at a certain position in large time and stuff like this. We can start taking limits and we can start taking expected values. But for now, we just want to get familiar with computing probabilities. And as I mentioned in the previous uh, lectures, that this lecture we will now deal with a more general case, and what we want to do now is establish the linear algebra. And just to step back and see where we're at, is I have this correspondence. On the left hand is a stochastic process, and with the Markov property. Here, recall stochastic process is a random variable that's evolving in time due to some random forces. And in this case, for the Markov chains, we're only considering a finite state space and discrete time. And we assume that we have the Markov property, meaning that the the conditional probabilities only depend on the most recent history or most recent information. And whatever happens before that doesn't matter, doesn't affect our conditional probability. So this is the object that we want to study and we want to think about. And what we did in the previous lecture, what we started to set up, is this correspondence to labeled graphs. So what we can do is we can take a Markov property, a Markov process, and we can represent it by a graph where the vertices are the elements of our state space, 1 through n. And then we have edges between states I and j. And we label these edges, or we give them a weight. This should be perhaps weighted. It's more appropriate. A weighted graph where the weight from edge connecting I and j, states I and j, is given by this function Pij, which is the conditional probability of this conditional probability, which really tells you the transition probability from going to from a state I to state j. So we have this correspondence. We've already discussed how to go this way. And got me again. These are supposed to be S's. And we'll see. We'll actually, at the end of the lecture, we're going to add an additional condition to make this correspondence precise. And it's going to be that P is a stochastic matrix. And the Markov property for on the left-hand side is really reflected by this weights and putting everything in the structure of G. And this stochastic property, the stochastic matrix property, it has to reflect the idea or the principle in probability that the probability of all the outcomes has to add up to 1. So just to this stochastic matrix property is just to make sure that we're in the setting of probability. Because you could imagine a scenario where we give the graph and then our weights, and we want to construct a Markov process, a stochastic process, but potentially we can give the weights where all the weights are add up, all the weights are 0. In that case, there's no probability, or all the weights are negative, or there's some positive and negative weights, then there's no probability interpretation of that. So to make sure that we're in the probability setting, we have the stochastic matrix property. But we'll come to that at the end of the lecture. In here, I gave a sample drawing of Markov of a Markov process or a label graph. I didn't do the labels. This should be P21. And notice the directions. I didn't write, in this case, the fact that I didn't write give an edge between label 1 and 2 in the direction from 1 to 2 implies that this transition probability is equal to 0. And the same is for P3 to 1, P1, 1, P2, 2, and so did I miss anything else? I think that's it. Those are the other edges that are not in there. And this is the second simplest non-trivial example. And you can start seeing that the dynamics start getting more intricate as we start adding states, vertices. Then you can have all sorts of arrows, and they can describe all sorts of scenarios. So this is the setting that we're trying to figure out now. And this is going to be now considering the more general setting, which of this Markov processes, which we want to think of them as weighted graphs. And in the previous lecture, we computed this for n equals 2. Now we want to compute this for n equals n. So in the general case. So this is the transition from state I to state j in 2 steps of our Markov chain. So again, the idea is to use law of total probability. I should keep my coloring consistent. So I and j. Let's go to the previous slide. J and I. Okay, so again, the idea is to do the law of total probability, and based on the n equals 2 case that we did in the previous lecture, we can graphically represent the law of total probability as follows. In this case, that we can get to from state I to state j, we can get to it through different cases, going through 1, going through 2, going through k, going through n finally. So these are all the possible paths, and we have to sum the weight of each path to get the total probability. So in here, the weight of this path, this is going to be transition of going from I to 1, and the weight of this edge is going to be going from 1 to j. And in general, what we're going to have is if we're going from here to here through state k, is that the probability of the first edge, or the weight of the first edge, is going to be the transition probability from I to k, and then the weight of the second edge is the transition probability of going from k to j. So this probability, by the law of total probability, is going to be given by this sum. And to write it in more of a matrix notation, then this is going to be this sum, p sub ik times p sub kj. And here we notice, what we have to notice now is that this is matrix multiplication. And in particular, this is multiplying p times p, the matrix p times p, we get p squared. And this is equal to the ij entry of this matrix P squared. And in the notation I like to use, I denote this as P squared. So the matrix P squared and the entry that goes from I to J. So this is gonna be in this notation that I use, I'm just gonna denote the power here, and then the entry ij of this matrix is gonna be denoted by this I arrow j. This is part of the reason why I like this notation better. It looks less cumbersome than this notation. And here I'm denoting the ij entry of P squared, and I denote the same thing. And this is it. This is how linear algebra starts playing a role in probability in Markov processes. A lot of the computations are just going to be matrix multiplication. And although by hand it's not all that convenient multiplying matrices, but this is something that we can do in a computer, and we can do it fast. And I encourage you to use computer to compute this powers of matrices. A lot of times we're going to do 3x3, 4x4. Doing it by hand is going to be difficult, but you just put in your favorite mathematical software and compute it. And this is how we're going to move forward. But let me now go through more examples and a little bit more explanation. So this is the first problem or exercise from the end of chapter 2 in the broad book. So we have this Markov chain, and again, the Markov chain is completely, or is characterized uniquely by these transition matrix. It tells you the transition probability going from state I to state J. And we have the Markov property, so this nails it down completely. So we have this transition probability, and these are the states 1, 2, 3, 1, 2, 3. Whenever we don't write the states, it's understood that the ith column stands for the ith state, and the jth column stands for the jth state. So, and here we have this initial distribution, which really means that probability that x, they're using here x for their Markov chain, x0 is equal to 1, is equal to 0.2, probability that x0 is equal to 2 is equal to 0.3, probability that x0 is equal to 3 is equal to 0.5. Note that all the probabilities add up to 1, because at time 0 you have to be somewhere. Now, I'll give you a moment to try to compute these probabilities. And in fact, you can, if you want longer than a minute, I encourage you to pause the video right now and try to compute this. And in the following discussion, we're going to go through the solutions. All right, spoiler alert, here we go. So for the first problem, we want the transition probability of going from 2 to 3 in one step. So in here, this is given by P1. It should be in here, this is equal to P1. The power of the P tells you the number of steps. And here is from 6 to 7, so it's P1, and it's from 2 to 3. So here, I just look at the second entry, at the entry 2, 3, which is given by this, so this is it. So this is P23. This should be very clear. It's just reading off the transition matrix. Now let's go to part B. And here we're given more conditions. So at time 9, we're at position 2, given these conditions. But here we use the Markov property. Here. Markov property. And we know by the Markov property, our probability, our conditional probability only depends on the most recent information. And here, if we look at 1, 5, and 7, the different times, the most recent one is this one. So we can forget about this due to a Markov property, and we're computing this. And now, this is the transition going from t to t plus 2, which we did earlier in the lecture. And we saw that this is just going to be the 3-2 entry, 3-2 of p squared. In my notation, I write this p squared 3 to 2. So what I do, I take the square of this matrix, or I take the product of this matrix with itself. I did this using Mathematica, and I obtained this result. And then I look at the entry 3-2, this and this. So, and this is going to be my answer. I'll let you look at it for a second. So here we start seeing how linear algebra comes in. Now let's do part C. Part C, it's a little bit more involved because they're trying to trick us, they're trying to flip the order of the times. And whenever to flip them back, what we do is we use base rule. So this is base. To flip it. So we can flip this, and then we have to multiply by this relative probability. So this first term, this is a transition probability, which we compute here. Sorry. The transition probability, I don't compute it anywhere, but this transition probability corresponds to the entry 3-1, because it's one time step, and it's the 0-3. So this is equal to this, and then probability that x0 is equal to 3, that is equal to this probability. This is 0.5, so that's this. And then the last thing that we need to figure out is the probability that x1 is equal to 1. So in here, to compute the probability that x1 is equal to 1, we essentially have to figure out all the possible ways that we can go to 1, starting at this configuration. So we start at configuration 1, 2, 3, and at time, so this is time 0, this is time 1, and we want to go this way. And this is going to have weight alpha 1, alpha 2, alpha 3. So this alphas. And then we have to multiply alpha 1 times the weight of this, alpha 2 times the weight of this, alpha 3 times the weight of this. And the weight of these edges are given by this numbers. So here, this is my alpha 1 times the weight of this edge, alpha 2 times the weight of this edge, alpha 3 times the weight of this edge, and I obtain this. This is the law of total probability. And doing this, so this is giving the distribution of our initial conditions, we figure out all the possible ways that we can arrive here to 1 in one step. So we obtain this. So this is the probability that x1 is equal to 1. And now we just look at this formula, we compute this is equal to this, this is equal to this, this is equal to this, and this is our answer, 15/17. So again, this is just using the matrix and reading the information. Now let's go to D. So now we're actually computing expected value. We use the definition of expected value. Then we use the law of total probability. Law of total probability. and then we compute. And here, we know that this is a two-step transition. So this is actually going to be given by p squared. And then you can recognize that this is matrix multiplication. This is a matrix, and this is going to be a vector, and this is going to be a vector. And the way that it looks is that this vector x0j is going to be given by this alpha vector. So it's this. And then this two-step transition is p squared. And then k represents a vector here. So you can convince yourself that these are linear algebra computations. And then in here, you can just put it into the computer, compute p squared, which is this, and then you have this vectors, and then just do the matrix product, and then you get this answer. I used Mathematica to get it. So again, these computations are simplified using mathematical software, and because we can recognize these operations as linear algebra. So that's A, B, C, and D. Now, going back to the original correspondence at the beginning of the lecture, and the question is, if we have a matrix P, does it always correspond to a Markov process? And I already gave some sort of hints for the answer. In general, it's not going to always give you a Markov process. We need to make sure that P is a stochastic matrix. And the idea, which is intuitive and it should be somewhat obvious after thinking about it, is that you want the sum of your probabilities to add up to 1. And you want your transition probabilities to be non-negative numbers and less than 1. So this is what we require, and it's given by two conditions. First, our transition probabilities from I to j, let's call it j, are going to be non-negative numbers between 0 and 1. This is going to be our coins. The coin that this is going to be a coin at side I, and this is going to be its bias toward, or maybe should be more of a die, so with the different n-sided die, and this is going to be the outcome of the die. And then we have that the total probability has to add up to 1. So here, the drawing, the graphical interpretation is, if you're in state I, then the transitional probability of going to 1 to 2 and all the states up to n has to add up to 1. So if you're in state I, you have to move somewhere. And somewhere in here, we also have I also. So meaning that you have to go somewhere, it means that you have to go somewhere else, either one of the other states or stay in the same place. But so all the weights, the sum of all the edges emanating from I should add up to 1. So this is going to be the key property, and the sum of all of these is equal to this transition, the sum of this transition probabilities, where I is fixed, and you go over all the possible future locations, which in terms of the matrix, you're adding up this row, and it has to equal to 1. So in particular, a matrix P is going to be stochastic if the entries are non-zero. Matrix P is going to be stochastic if the entries are non-negative and between 0 and 1, corresponding to probabilities. And if all the rows add up to 1, meaning that the total probability is equal to 1, the probability of transition is equal to 1. So these are the two conditions, that they add up to 1 and that they're between 0 and 1. And then in that case, if we satisfy this condition and this condition, we call P a stochastic matrix. And then you can do the graphical representation, and then you have a Markov process. So this completes the correspondence between Markov processes and weighted graphs, weighted directed graphs. And you have to have the transition matrix to be this P. And this weighted graph, really, you can just represent by this stochastic matrix. So now we have the correspondence of a Markov process is one-to-one with stochastic matrices. And in this case, actually, I'm thinking about discrete time and finite space. And these are what people like to call Markov chains. They're in correspondence with this finite matrices that are stochastic. So let's consider a specific example. Give a Markov transition matrix for random walk on the weighted graph in figure 210. All right, so this is the 8th problem or exercise from the back of the chapter 2 in the broad book. In here, you'll see this notation. In here, we don't have a direction in the edges, but in here, when we don't have a direction, we just assume that this an undirected edge is a edge going both ways, one with one and one with the same label. And in here, oftentimes you'll see these graphs that are not normalized for the probability to equal to 1. So in here, if we see, for instance, A can go to B with weight 1. And it doesn't go to A by itself. It can go to C with weight 3. And it can go to E with weight 4. And now these weights don't add up to 1 clearly. So what you can do is to normalize them to add up to 1. So it's 1 plus 3 plus 4, that's 8. So I divide by 8. And so now I have the top row of my P matrix. It's going to be A, and then A, B, C, D, E. And then I'm going to have A, B, C, D, E. And then here, I can add the weights given here. The rest of the weights are 0, A 0, and D is 0. And I have that this is 1/8, 3/8, and 4/8. And then I continue doing that for the rest of the edges. And again, if they're undirected, I just assume I have 2 edges and they have the same weight, 2, 2. So I just continue doing the same type of procedure. And after doing that, I get this answer. So this first M matrix, I just obtained it by reading 1, 3, 2. Oh, this is supposed to be a 2. So I take this back. 3, 2. And then it adds up to 6. Good thing I already had the answer. And this is 2. 6, 6, 6. Okay, so in here I have this graph, and then I can create the incidence matrix, or the matrix of the weights. And here this is 1, 3, 2, and these weights are not normalized. And then I normalize each of the rows so that they add up to 1. Again, remember, since these edges are not directed, then I always assume that it's symmetric this way. So I'm going to have, all the edges are going to be symmetric. So this is reflected by the fact that this matrix M is symmetric about this diagonal. So this is symmetric with this is symmetric with this, symmetric with this is with this is with this is with this is with this. So everything's symmetric. So you'll see that. So if you see a symmetric matrix, you have to think of something like this, where the edges are undirected. But in any case, now I want to normalize each row so that it's a stochastic matrix. This adds up to 6, this adds up to 10, up to 6, 2, and 6. And then I divide each row correspondingly so that each row adds up to 1. Then we have that P is a stochastic matrix. So this is playing on this idea that we have these different interpretations or representations of the Markov process. It could be a stochastic process with the Markov property. It could be, it also corresponds to this transition matrix, to a stochastic matrix, and it also corresponds to this weighted graphs. So we can think of it as 3 different ways. A lot of times it's good to actually have a drawing to kind of try to figure out things and get a concrete grip on the problem and have an interpretation with a picture. And in this problem, we went from the interpretation of the graphical interpretation to the stochastic matrix. And these are the 2 major interpretations that will be used. The definition, the stochastic process plus Markov property, is just the foundation, the theoretical definition. And then if we want to work practically with the Markov process, we either need the graphical representation or the stochastic matrix, the transition matrix. Let me do one more example. Problem 17 from the back of chapter 2 in the Bro. And this is again asking about the properties of this stochastic matrix P. Again, the stochastic matrix has 2 properties. The entries are non-negative and between 0 and 1, and the rows add up to 1. And we want to show that lambda equals 1 is an eigenvalue P, and what is the associated vector. So let me first start with spelling out the properties. Stochastic means that the rows add up to 1. So this is the first property. And I already know the answer. This is hindsight. And it's using this property that I'm going to find the eigenvector. So from hindsight, I already know that this is going to be my eigenvector, where it's a column vector with all entries equal to each other. And to make it a probability vector, I just chose 1 over n, but as long as they're all equal to each other, that's fine. So every entry is equal to 1 over n. And then I compute the product of P times V. And what I want to show, that P V is equal to V to show that the eigenvalue is equal to 1. So I compute PV and look at the I entry. And this is going to be this matrix P from I to J and V sub J. And V sub J is actually, this is 1 over n. And this is 1 over n. So in here, by the definition of 2, this I can write this as 1 over n. And then using this, and then I can factor the 1 over n out. And then using this stochastic property, I know that the sum of the p's over j is going to equal to 1, so I get 1 over n. So I have that p times v is equal to v, so I have that lambda 1 is an eigenvalue with eigenvector v. So this is the answer, and it works through hindsight. I got the black lung. Nothing coffee won't cure. And this is the end. Or is it? Well, the end for this lecture series. We will now move on to, we will next move on to the third chapter of the Bro. We'll start doing more involved computations with Markov chains. This is just a setup of what is a Markov chain, the first principles, and trying to get us comfortable using linear algebra to compute probabilities. And yeah, thanks for showing up.